Hey guys, welcome back to eGate Tutor. In this video, let's talk about maximum shear stress theory, which is sometimes called as Tresca's, Coulomb's or Guest's theory in the topic theories of failure. Let's start the discussion by first looking into its statement. According to maximum shear stress theory, failure of a component which is subjected to biaxial or triaxial state of stresses occurs when the maximum shear stress at any point in the component equals the maximum shear stress in the standard specimen in a simple tension test when yielding begins. Well, that is a statement of maximum shear stress theory. Let's get into a few mathematical aspects of this theory of failure. As we all know, the standard specimen which is generally used in the simple tension test on universal testing machine looks something like this. So since it is a simple tension test, let us assume that this specimen is held in the universal testing machine which is subjected to a uniaxial pull. Let us assume that this is the x direction and this is the y direction. When the standard specimen is subjected to only uniaxial tension, representing that on a biaxial state of stress system, it is represented in this way where there will be only one stress which is sigma xx and all the other stress components of a biaxial state of stress system will be 0. The other stress components are sigma yy which is 0 and tau xy which is 0. Now for this kind of loading, when we calculate the principal stresses using the formula sigma 1 comma 2 is equal to sigma xx plus sigma yy by 2 plus or minus under root sigma xx minus sigma yy by 2 whole square plus tau xy square. In this, when we substitute these conditions and when we calculate the principal stresses, we get the principal stress sigma 1 is equal to sigma xx and the other principal stress sigma 2 will be equated to 0. Now let us try to calculate the radius of Mohr's circle. This is given by the term which is in the square root in the equation of maximum principal stress and minimum principal stress. So radius of Mohr's circle is given by tau max. The radius of Mohr's circle equals always the maximum shear stress and it is calculated by the formula square root sigma xx minus sigma yy by 2 whole square plus tau xy square. Since for the considered biaxial state of stress system, this radius of Mohr's circle, or in other terms the maximum shear stress, becomes sigma xx by 2. But we all know that sigma xx is equal to sigma 1. So this can be written as sigma 1 by 2. From the statement, when the yielding starts, the applied load, which is the maximum principal stress, will be equal to the yield stress in tension. When we replace this in the previous equation, the expression for maximum shear stress becomes sigma yt by 2. Therefore, the maximum shear stress theory predicts that the yield strength in shear is half of the yield strength in tension. So when that is considered, this can be written as the yield stress in shear is equal to yield stress in tension divided by 2. Let us consider a system where three principal stresses act, that is, when the component is subjected to triaxial loading where the principal stresses are sigma 1, sigma 2 and sigma 3. We know that the shear stresses can be written as the combinations of these principal stresses and they can be listed as, when we write the component for tau 1 2, this is equal to sigma 1 minus sigma 2 by 2. Similarly, when we write the component of tau 2 comma 3, that is sigma 2 minus sigma 3 by 2. Similarly, when we write tau 3 1, this can be written as sigma 3 minus sigma 1 by 2. So according to the statement of maximum shear stress theory which we have seen just now, it states that maximum of tau 1 2, tau 2 3 or tau 3 1 should be equal to the yield stress in tension divided by 2. Let us assume that among these three, for now let us assume that among these three shear stress components, let us assume tau 1 2 is maximum. When we also include the factor of safety, the equation becomes sigma 1 minus sigma 2 by 2 is equal to sigma yt by 2 times factor of safety. This can be further written as sigma 1 minus sigma 2 is equal to the yield stress in tension divided by factor of safety. Similarly, when we take the other two shear components, this equation can be written as sigma 2 minus sigma 3 is equal to the yield stress in tension divided by factor of safety, and sigma 3 minus sigma 1 is equal to the yield strength in tension divided by factor of safety. So these three equations can be considered depending on the component of shear stress which is maximum. The expressions which are written in the boxes here are generally used. These are used to determine the dimensions of the component which is to be designed. For time being now, let us ignore the factor of safety part and let us rewrite the equations for the shear stress or the failure criteria according to maximum shear stress theory. In that cases, if tau 1, 2 is maximum, the failure condition becomes sigma 1 minus sigma 2 by 2 equal to the yield stress in tension divided by 2. This can be written as sigma 1 minus sigma 2 is equal to sigma yt. Similarly, if tau 2, 3 is maximum, this equation becomes sigma 2 minus sigma 3 is equal to sigma yt. Similarly, if tau 3, 1 is maximum, this equation can be written as sigma 3 minus sigma 1 is equal to sigma yt. Remember that in all these three conditions, we have taken only the tensile yield stress. What if the material is loaded in compression? So in that case, these equations become sigma 1 minus sigma 2 is equal to minus the yield stress in compression, sigma 2 minus sigma 3 is equal to minus yield stress in compression, sigma 3 minus sigma 1 is equal to minus the yield stress in compression. Remember that these are the design equations or failure equations when the material is loaded in compression. You might get it out why is a minus sign used here. It is according to the sign convention that all the tensile forces acting on the component are considered to be positive. All the negative forces acting on the component are considered to be negative. Since compressive forces are negative, the yield stress in compression is considered to be negative. So combining the equations in tension and compression, writing these equations in a generic way, we get combining the equations in tension and compression, writing these equations again in a generic way, we get sigma 1 minus sigma 2 is equal to plus or minus the yield stress, sigma 2 minus sigma 3 is equal to plus or minus the yield stress, and sigma 3 minus sigma 1 is equal to plus or minus the yield stress. Next comes the important aspect of maximum shear stress theory, which is the region of safety. So as we all know, the region of safety is constructed for the biaxial state of stress system where the third principal stress is considered to be 0 and the principal stresses sigma 1 and sigma 2 are considered as the coordinate axis along the x and y respectively. So along x, sigma 1 is considered and along y axis, sigma 2 is considered. So when we take the condition of sigma 3 is equal to 0 in the generic set of equations, those equations become sigma 1 minus sigma 2 is equal to plus or minus sigma y, sigma 2 is equal to plus or minus sigma y, and sigma 1 is equal to plus or minus sigma y. Also, it is very important to note that if there is any equation in the form x minus y is equal to minus a, this indicates a straight line in the second quadrant with minus a as intercept on x-axis and plus a as intercept on y-axis. So this becomes the equation of straight line in second quadrant with minus a as the intercept on x-axis and plus a as the intercept on y-axis. So similarly, if we have an equation of the form x minus y is equal to plus a, so this is the equation of a straight line in fourth quadrant where plus a is the intercept on x-axis and minus a is the intercept on y-axis. Now let us consider the first step in the first quadrant. We all know that in the first quadrant both sigma 1 and sigma 2 are positive. In such cases, Now let us assume that sigma 1 is greater than sigma 2. In that case, the equation becomes sigma 1 is equal to the yield stress in tension. That is represented on the region of safety along this line PQ. Now let us assume in this quadrant that sigma 2 is greater than sigma 1. In that case, the equation becomes sigma 2 is equal to the yield stress in tension. Therefore, this condition is represented on the region of safety in this way. Let us note this point as R. Now let's move on to step number 2, which is along the quadrant 2, where sigma 1 is negative and sigma 2 is positive. In that case, yielding occurs if sigma 1 minus sigma 2 is equal to minus yield stress. Comparing this equation with this equation, it is nothing but this is the equation of a straight line in the second quadrant with minus a as the intercept on x-axis, where minus a here is minus sigma y. So when we represent that on the region of safety, it is represented in this way. Let us note this point as T. This point is minus of yield stress in tension, and this point is plus yield stress in tension. Remember that in this conditions we choose, we take the yield stress is equal to the yield stress in tension. Now let us move on to step number 3, where we will focus the region of safety in quadrant 3. In quadrant 3, both sigma 1 is negative and sigma 2 is also negative. In such case, let us assume that sigma 1 is greater than sigma 2. In that case, the equation is sigma 1 is equal to minus of the yield stress in tension. So that is represented on the region of safety in this way. Let us assume this point to be noted as U. Similarly, if sigma 2 is greater than sigma 1, the equation becomes sigma 2 is equal to minus yield stress in tension. So that is represented on the region of safety in this way. Let us note this point to be V. Finally, let's move on to step number 4, where we will focus on quadrant 4. In quadrant 4, we know that sigma 1 is positive and sigma 2 is negative. In such case, the yield criteria according to maximum shear stress theory becomes sigma 1 minus sigma 2 is equal to sigma yt. When we compare this matches with this equation, where x is equal to sigma 1, y is equal to sigma 2, and plus a, which is the intercept on x-axis, is equal to yield stress in tension. So when we represent this particular criteria on the region of safety diagram, we get a straight line. Therefore, according to maximum shear stress theory, this becomes the region of safety. Since we have assumed that the yield stress in compression is equal to the yield stress in tension, the region of safety according to maximum shear stress theory can be considered as a hexagon. Remember, this is valid only if sigma yc is equal to sigma yt. If the point with coordinates sigma 1, sigma 2 lie inside the region of safety as point A, which is indicated here, the component is considered to be safe and failure may not occur. But if the point lies outside the region of safety as indicated here by point B, the component may fail. There is another important concept here which is to be noted, that is the concept of shear diagonal. We all know that shear diagonal is the locus of all points which corresponds to the state of pure shear stress. That is represented on the region of safety for maximum shear stress theory in this way. So this is considered to be the shear diagonal. When the component is subjected to pure shear stresses, we know that the principal stresses are equal in magnitude but opposite in sign with a magnitude of shear stress. So from this we can write sigma 1 by sigma 2 is equal to minus 1, which implies sigma 1 by sigma 2 is equal to minus of tan 45 degrees. So that is the reason why the shear diagonal makes an angle of minus 45 degrees with the sigma 2 axis. It is to be remembered that shear diagonal is also called as the line of pure shear. And coming to the most important point of maximum shear stress theory, the maximum shear stress theory is widely used in predicting the failures of components or structures which are made of ductile materials. Maximum shear stress theory gives very good predictions when it is applicable to ductile materials. In most of the cases, the maximum shear stress theory is considered to be the default theory of failure which is used in designing the sizes of the components. Now let us look at the general procedure to solve questions from theories of failure. The first step is to write down the given values. These given values could be either sigma x, sigma y, tau xy, or yield strength in tension, ultimate strength in tension, and so on. So these can be the given values. Next step is to write down what is to be calculated. So whenever the typical questions from theories of failure appear in GATE exam, we will be generally asked to calculate either factor of safety or diameter of a particular machine member or something like that. So these will be the values which are to be calculated. The third step will be to make a note of theory of failure to be used. So whenever a question is appeared in third step is to note down what type of theory of failure is to be incorporated. It can be either a maximum principal stress theory, it can be either a maximum shear stress theory, it can be maximum distortion energy theory, and so on. So it is very important to make a note of which theory of failure is to be incorporated to calculate the unknown from the given question. Now the fourth step in the general procedure is to write down the design equation or the failure condition according to the selected theories of failure or given theory of failure. For suppose if the theory of failure is maximum principal stress theory, the design equation or failure condition generally is if sigma 1 is the maximum principal stress, then sigma 1 should not exceed the yield stress in tension divided by factor of safety, or sigma 1 should not exceed sigma ut divided by factor of safety. The last step is to substitute all the given values design equations and to calculate the unknown parameter. It is that if the state of stress system is given in sigma x, sigma y, and so on, it is always recommended to calculate the principal stresses for the given type of loading, because most of the theories of failure will only use principal stresses in their calculations. Now let's solve a problem to understand the solving procedures when a question from the theory of failure is given. A machine element is loaded such that sigma 1 is equal to 120 megapascals, sigma 2 is equal to 0 megapascal, and sigma 3 is equal to minus 90 megapascal. The yield strength in tension and yield strength in compression both are equal to 360 megapascal. The factor of safety according to Tresca's theory is. It is important to note that Tresca's theory is nothing but maximum shear stress theory. Let's move on to the solution. We are given with sigma 1 is equal to 120 megapascal, sigma 2 is equal to 0 megapascal, and sigma 3 is equal to minus 90 megapascal. Now we have to calculate the maximum shear stress. Maximum shear stress is nothing but the maximum value of absolute value of sigma 1 minus sigma 2 by 2, or sigma 2 minus sigma 3 by 2, or sigma 3 minus sigma 1 by 2. So now let us substitute the given values here. 120 minus 0 by 2, 0 minus minus 90 by 2, minus 90 minus 120 by 2. So clearly from this we can understand that this is the maximum value. Therefore the maximum shear stress is equal to 210 by 2. Therefore, according to maximum shear stress theory, the failure criteria is tau max is equal to yield stress of the material divided by 2 times factor of safety. So from this we can write factor of safety is equal to sigma yt by 2 times tau max. we are given with the yield strength in tension as 360 divided by 2 into 210 by 2. So simplifying this, we get 1.7 as the factor of safety, which is option A. That's all from this video, guys. Thank you for watching the video. Please like, share and subscribe to our YouTube channel eGay Tutor.